So we're going to finish up our discussion of MapReduce, which is, in the context of distributed computing on a cluster. And then we're not going to do a review today, but I'll just give you some basic information about kind of how to start studying for the exam, so that you at least know what you don't know before Monday and when we do the review. Okay, so we were talking about this problem of, say you have an entire internet worth of data, like Google does, and you need to answer some question about that data. Doing it on one machine is just absolutely not going to work, so you distribute it to a cluster or many clusters, and then part of the problem becomes a big part of the work is how do you do that distributing and how do you track who's working on what and getting the results back. So there's like a whole machine just dedicated to doing that, like a job server. And one of the models we looked at was where instead of the workers kind of asking for work, you have this one machine that is primarily responsible for assigning tasks, tracking who the workers are, what is their progress, and that by itself is a big job when you're talking about 2,000 machines and 200,000 jobs. And then another big job is, once you've split the work up, you're now going to have split up results, partial results from each of those machines. How do you get those results back and then aggregate them in some way? Okay, so MapReduce is the specific tool and kind of ecosystem that we talked about, one of the ways to address these problems. So it's a programming model plus the system, the underlying libraries and kernels that run on the cluster and run your mapper and your reducer. So basically the programming model is you write map and reduce, that's just two functions. So that's the user's part of it. And then the system takes care of like everything in between. So you say here are the list of say 1 million files or whatever where all of the data is. Here's the map function, here's the reduce function, and then the system automatically goes and distributes the work, calls the mapper appropriately, calls the reducer appropriately. So what is map and reduce? Kind of what does that name mean and what do these functions mean? Basically, the map part is the first big filter. So you apply some function to your part of the input. So the simplest way to think of this is, say you have 1 million files, then the easiest way to distribute that is make one file be one job. So your one part of the input is a file, and you want to count the number of occurrences of every word in that file. It's like how many times does the word the occur in some file? And then you have tons of machines doing that for different files. And then the reduce part is, so once every machine has come up with their partial or local counts, then the reduce part is you just apply some other function that aggregates those. So given like, this machine said the word the occurred 15 times. This machine said it occurred 5 times. You take all of those partial results and add them up or average them or whatever your aggregation is. Okay, so kind of specifically looking at that, this is the classic example for explaining MapReduce. It's a little simple, so try to imagine there are bigger problems here, and we'll talk about other uses of this. But just to give you the idea, so say file 1 has to be or not to be. File 2 and file 3 have just some other text in them, and the goal is we want to know across all these files how many times does 2 show up, how many times does B show up. So just count every word. So the map phase, for file 1, you'll get the word 2 with a count of 2, the word B with a count of 2, and so on. So those counts are the output of map. And then the system collects all of those results, gathers them, and generates this intermediate step where we have a key of the word 2 and a value of all of the partial counts. So 2 showed up twice in one file and once in another file. B showed up just twice in one file. And then that becomes the input to reduce. So you have these keys now. The keys are now, the jobs are for an individual word. Instead of the original jobs were each file, now the reduce jobs are for each word. How many counts are there in each of these lists? Okay, so 2, the word 2 is just, it showed up 2 plus 1 times, or showed up 1 plus 1 times, and each of those counts came from a different file originally. Okay? So here's a little more interesting example. Say you want to find the average rainfall per month. So what is the average rainfall for January? And you have all this information distributed by cities. So Atlanta, SLC, say there are thousands of cities. And so you have, say, let's look at the Atlanta file. For January 96, there were 8.26 inches. For January 97, there were 7.88 inches, and so on. So pretend this data goes back 100 years, and you have 1,000 files or more, and you want to find total average rainfall for January. Okay? So the map phase, each job for the map phase is one file for one city, containing 100 years of rainfall data. So you run each file through a mapper, and it will come up with its own partial average for January. So it's the average just for that city. So each of these 3 things will run on one mapper. And I'm only showing 3, but there are, say, thousands. Okay, so you'll get thousands of partial January rainfall averages. Then the system, so this is not map or reduce, this is the system's job, takes all of those outputs from every individual mapper and gathers, sorts, and then that's how it will decide how to redistribute them to the reduce phase. So it's going to sort them based on the key. So the key now that we're outputting is month name, followed by an average. So there will be just 12 keys, but there will be thousands of averages, thousands of January rainfall averages. And the system collects all that and puts it together into this key list pair. Then that becomes the input to the reduce phase. So now we only have 12 reducers, one for each month. Each reducer gets a giant list of averages corresponding to its own month, and it applies some function, which again is just an average. Okay. So kind of more in the context of like if you're going to program this thing and actually run it on some giant cluster. For the map phase, the input is key value pairs, where the key is a file name and the value is the file. So this is how we define what the input is. And then the output of the map phase is key prime value prime pairs. So prime just means they're still keys and values, but they're in a different domain. So the domain of the original input is file name and file contents. The domain of the output is whatever key you're extracting out of each of those files and whatever value you've extracted for that key. So as an example, January plus a number, February plus a number. Okay. And that's automatically distributed across every machine in your cluster. And then the gather sort phase, done by the system, it takes all of your key prime value primes and finds all of the key prime that are the same. So there will be a lot of, say, Januaries in there, and then makes a list of all of those value primes. Okay, so we went from key value to key prime value prime because we're dealing with just one mapper at a time. Then you take all of those mapped results and you get key prime list of value prime. Okay? And this is assuming that there will be some keys in common out of all of those mappers, and that's the basic idea, is there will be. So, and then that becomes the input to reduce. So for every reduce job, I'm going to have a key plus a list of some kind of value in the new domain, the post-filtered domain. Okay, and the output is just a value. Question?
So I know this is a simplified example, but in real life, do they only do this with like files and the file? Can you kind of tell the system what type of data you want to get out?
Yeah. So in the real, in the real MapReduce world, yeah, you basically have to figure out how to put your data, how to spread your data across many files. It doesn't have to be a text file, but so it can be any data you want. But yeah, that's the basic way of spreading the data out, is because you assume you have so much data it's not going to fit on one disk. So you have thousands of disks in some cluster, and that's kind of how you divide up the work. Really, though, the work is probably already divided up. If you somehow had a giant data set that you needed to figure out how to split up into files, that's kind of a different challenge. And usually MapReduce is, the data is already split up into multiple files because you have so many servers doing their own thing. Okay, so the idea is there are usually many more map jobs than reduce jobs because the mapper has already filtered it down to some subset of keys, key prime that you're interested in, and that will, by definition, be fewer than the number of input jobs. So the programming model here is you basically write two functions. You write map and reduce, plus a little bit of like config and setup stuff to tell it how to run where the data is. But then the system just kind of automatically knows about all of the workers, knows how to efficiently assign tasks and get results back, gather them, sort them, redistribute them for the reduce phase. And all of the smarts are basically in the system. It makes it super easy for you to just say map and reduce. So as an example, here's the word count example in actual code, pseudocode. You write a function map. The input is file name, file contents. So that's key value. And you just, for everything in that file, if we're dealing with text, which we are for Wordcount, you can imagine there's, some kind of split on the words, like split on white space or whatever, which I'm not showing, but that's trivial. And then there's this function, this is an actual MapReduce function, emit intermediate. So that is, you're emitting the output of the map phase. That's why it's called intermediate. So if W is the word, then I emit a W with 1, saying just increase the count of W by 1. And the reason we do it this way, you don't have to do it this way. So I'm emitting a new key prime with a count of 1 every time I see a word. Instead of, I could go through the whole file and keep track of my own count, make my own dictionary, say like, okay, the word the showed up 5 times in this file. So at the end, you would then emit the with 5. Doing it this way just means you don't have to save your own state. Let the MapReduce system save its own state. The end result is the same. Okay, so the inputs here were key value pairs. The output, W and 1, those are the key prime value prime pairs. And then reduce after all of those key prime value primes have been collected and put into the list, is you write your own reduce function. You're going to work on one key. And so in the word count example, we just loop through every intermediate result, so all of those counts for whatever key, whatever word, and we just add them up. So total plus equals, that's doing a total sum. If I was doing an average, there'd be some divide here at the end or whatever. Write any code you want. It's your own custom aggregator. Okay? And then finally, at the end, you just do emit. So that's, instead of emit intermediate in the mapper, you do emit in the reducer because that's the final answer for that key. Yep?
So the job gets done, doesn't have to wait for all the other jobs to get done?
If a job gets done, does it have to wait for all the other jobs to get done? Ideally, there will be, if one server finishes fast, there will be another job for it to start working on. The general idea is you have a lot more jobs than machines. So any given machine will probably do like 100 or so maps.
And who combines the results?
And who combines these results? The system does. So the MapReduce system will kind of collect all of these results, partial results from all of the workers, and dump them out to a file for you.
How does it know when it gets done?
How does it know when it gets done? Yeah, so we'll kind of get to how all this stuff works in a little bit. But basically, the one master server is responsible for knowing all of that. But I'll get to those details in a minute. So I want to talk about how this has been specifically used at Google. Google was Google was the first kind of major proponent of this. They have since, I think they still maybe use it a little bit, but they've since moved on to other techniques for some of their big distributed computing jobs. But these are real examples from Google, real problems they've solved with their massive amounts of data and massive clusters. So grep is just a regular expression matcher. It'll go look through some file, or in this case, thousands of files, looking for a word, or looking for a regular expression. Okay, so imagine you have tons and tons and tons of web logs or something, and you want to look for one particular URL out of all of those files. Weblogs stats, so again, tons of weblogs, and say you want to know if they Googled for a certain term, what was the URL that was most clicked on after searching for a certain term. So you know, like which one do people think is most relevant, or something like that. So what they try to target for mapping and reducing is roughly 64 megabyte jobs. So each file that's input to a mapper is going to be about 64 megs. And if you break that'll result in M tasks and R reduced tasks. The basic goal, sometimes it doesn't always work out this way, but the basic goal is if you have 2,000 machines, you want 200,000 map tasks. So about 100 times as many jobs as machines for the map phase. And then 2 to 5 or 2 to 10, something like that, as many, 2 to 10 times as many reduced jobs as machines. And the reason for this, why do we want so many more jobs than machines? This just reduces the probability of one of those jobs being way longer than the rest of them. And that is what's going to slow down a distributed workload. Like remember the prime numbers example? You have one job working on all the large primes, one server working on all the large ones, and one working on the small ones. You don't really gain any parallelism. The other issue is, so not just for distributing the workload, but also kind of fault tolerance. If one of those jobs fails, then you haven't lost a ton of work. Like if a job is only 10 minutes or less than an hour or something, then at most you're going to lose an hour of work if the machine fails. So what if the master machine fails, though? There's like one machine that's responsible for assigning all these tasks. If it fails, basically what they do is it writes checkpoints every so often. Anytime it gets some kind of concrete result back, it will save that permanently. And then if the machine fails, you can just pick one of the other ones to become the master and reload that checkpoint and restart the job. You will lose some work, but not all of it, depending on how far back your most recent checkpoint was. So one example, so this information all comes from this talk that some Google engineer gave. They were working on this giant job, and during the middle of that, 1,600 out of 1,800 of their machines failed. Probably due to something like the cooling system went down in that server room, so they had to shut all the machines down. But 200 of them remained running, and the job still finished. It obviously got slower, it took longer, but it can automatically just robustly handle any kind of failures like this. And then, so finally, what if, even if you do successfully split up the work into roughly equal-sized chunks, you can still have one machine that's just particularly slow, like if its hardware is almost failing, and you have to like retry disk reads a bunch of times, or if the OS is in some bad state, like has a bunch of fragmentation or something. What Google does, and what probably most MapReduce implementations do, is like near the end, if there are one or two jobs that are still running and only a few machines actually working, it'll just take those jobs and give them out to a bunch of other machines and just let them race to see who wins. And one of them will probably be running at full speed, and you'll get the result back before the slow one, and then you can just kill the slow one. It's kind of back to the question of what happens when there's a failure, or how do you know that some machine is going too slow or taking too long? They basically phone home every once in a while. So they'll ping the server, or the server will ping them. If there's no contact after a certain amount of time, the server assumes that that worker has lost power, disconnected, or whatever, and it knows what job it was working on, so it just goes and assigns it elsewhere, or puts it back in the queue. It's all very fault tolerant, and this is the kind of thing that if you tried to write this on your own, and you did it in some way such that like if one machine fails, all your data is bad, and it takes a day, then you have to restart this day-long job. So, nothing like super technologically impossible here, but if like trying to do this on your own is like trying to write a program in assembly language. There are all these tools to make programming easier. This is a tool to make distributed computing easier. It just handles all the nasty stuff for you. Okay. So any questions before we kind of look at actually what this looks like? Yeah.
So as far as the data actually being stored, the file types, I'm imagining this data is probably stored in some sort of database. So are those just specific file types that explain the data in a certain way that the system knows about?
Yeah, so as far as how is the data stored, it's not actually even necessarily in any kind of database. It could just be a giant directory somewhere with a whole bunch of files in it. But this directory is distributed. The file system is distributed, so any one machine is actually only holding certain parts of that directory. And it's all tolerant to any particular drive failing because some of the data is replicated. And, there's something kind of like RAID. As to like how and where the data is stored is MapReduce is kind of agnostic to that. You just kind of tell it where to get the data, how to get the data. But I believe it has to be, you kind of have to pull it out into just a whole bunch of files. So if your data was originally in an SQL database, you'd first do something like get all the data out, dump it to a bunch of files, then run MapReduce.
How does a backup come into play with all of this data being stored? Is it backup phase happen when it's doing the mapping, or is it like a secondary thing that?
So how does
once it's all
backup happen as far as recovering from failures?
As in, like, when it's trying to do all these mapping and storing phases, is it trying to store it to 2 locations so that way you have a copy of it?
Yeah.
Or is
So,
it like it'll duplicate it after it's done?
So how do you, when you're getting these temporary results back from all these machines, how does it save it in a robust way? Basically, this all comes down to the problem of a distributed file system, which is kind of a separate issue, but this has been solved in many different ways. You have a cluster of machines and a distributed file system. If you write a file somewhere, it's automatically going to be replicated and kind of split up in such a way that if you have one disk failure, you can always recover and reproduce the results. So the fact that one master machine is taking care of like all of these temporary file writes, it's doing so in a way that any file written is backed up and robustly written, spread across many disks. That's separate from MapReduce, though. Okay, so I have MapReduce running on my own machine. I don't have a cluster, unfortunately, so it's going to be running MapReduce on a cluster of 1. But just to kind of give you an idea of how to run it, what it looks like, what the results look like. I have here, so Hadoop is an organization that kind of took over Google's implementation of MapReduce and made it more publicly available. As an example, one of the examples they hand out. So here's a directory with just a whole bunch of XML files. These XML files might be the input that you might want to ask some question about, like what XML tag occurs in which files, or which one occurs the most, or whatever. So let's just look at like one of these. I don't know, KMS site.xml. So lots of English in here, just kind of words. It doesn't matter that this is technically a comment. If we're treating this as words, then it's just going to be white space separated. So here's a word licensed under the so forth. Oh, this is actually a tiny file. But here's a word, this in XML tag configuration that would be treated as a word. So you kind of have to know what format you're looking at. Some of these other files are big, and it's not a realistic example because I don't have terabytes of data that I can work with here. But as an example, let's just do the word count. What out of all of those XML files, count every word and how many times it appears. So here's the command. Don't really worry about, this is just how you run MapReduce. This is a Java implementation, so I'm executing a jar file. But here's kind of the part that's showing what we're doing. I'm running the word count demo. Hadoop input is the input directory, and count example will be where it will put all of the outputs. So you have to imagine that this Hadoop input is on a distributed file system, has thousands of files in it, and the system's automatically going to use every file in there as one map job. Okay, so if we run that, just kind of prints a whole bunch of info about what's happening and what it did. That would, in a real job, would obviously take way, way longer. But what we get is, what did I call it? Count example was the output directory. And you get Sometimes you get the answer in parts. This one was so small, I get one part. So here is the result. So the word quote star quote appeared 19 times out of those XML files. The word parentheses root occurred once. So just kind of gives you every word count where if you're saying that a word is defined as separated by white space. So you get these things like where this is considered a word. But you could provide your own regular expression if you wanted to define what a word is. Yeah, the word count argument is defining which MapReduce program I want to run, which is already has been compiled in a place where it knows about.
So in reality, you would write that.
Yeah, I'll actually show you the code for that in a second. Here's another one. So now I'm running, instead of word count, I'm running the grep demo. So grep is search for a regular expression out of all those files. So I'm using the same input, all those XML files. My output will be grep example. And then this is the regular expression I want to search for. So I'm searching for the literal word license, optionally followed by a dot. Maybe I want to find all occurrences of that word for some reason. Or imagine, instead of that, I write a regular expression that matches any URL. So find all URLs out of all those XML files. So it does its thing. And then if we look at grep example / part 0, we get the word license without a period showed up 54 times, and with period showed up 18 times. Okay. So just kind of a simple example of how this would work. Here is let's see. There, okay, MapReduce / Wordcount .java. So here's the actual code for the word count demo. You write a class that extends mapper, which means it has to have a function called map. Okay, so there's my mapper. Don't worry too much about all this, syntax specific stuff. But let's just look at the map function. The input is a key, a key value pair. So I have that key will be a file name, and then the text value, that'll be the contents of that file. The context thing I didn't actually show. That's part of the mapper input. That's kind of just more information about how the system is running. So I make a tokenizer, and then I just do while that iterator has more tokens. I do context.write whatever word with a count of 1. And 1 is just defined right here as this int writable thing is kind of like a MapReduce thing. It's the number 1. This is just syntax specific. And then down here, here's my reducer, which extends a different class, which means it has to have a function called reduce. And now look, so the input is a key, but this is in the key prime domain, and then a list of values prime. And kind of works the same way. The particular reduction I want to do is a sum, so I just write code. I want it to start at 0. For every value in that iterable of values, I get the value, add it to sum, and then finally at the end just write the output. Okay, so don't worry too much about the syntax here. I'm just kind of showing the basic programming model. You write whatever Java code you want in Map, whatever Java code you want in Reduce. The inputs are what's hard here, and the inputs are what the system automatically sets up for you. And you have to think about it in terms of, although you are writing one function, and it kind of looks like you're just operating, you're never calling this function, you're not setting up the loop that runs this function a million times. You have to remember that this function is going to be run in parallel on many thousands of machines for one file input at a time. And same with the mapper. Okay? So any questions about that? Yes?
So one job takes on a file, or what's the unit of work?
The unit of work for the map phase is one file. The unit of work for the reduce phase is one key that has been emitted by the map phase. Key prime, I should say. So in this example, the input to the map is one file containing some text. The input to the reducer is one word. The key would be one word out of one of those files. Okay, so again, I'm kind of just like flying through this because you don't have a MapReduce assignment. You're not going to have to actually use this. I do want you to know kind of the basic idea, though. What are the problems, what are the challenges, and how are they overcome for big data in distributed computing? So let's take our break now.